All right, secondary educators, we have one last jump to make. Last time we built the rational numbers, and so once you build the rational numbers, it's time to build the reals. In the preview activity, I asked you for an increasing sequence of rational numbers that converged to 4/3, and that's not terribly difficult. Increasing sequence that converges to 4/3. This'll do it, right? And then an increasing infinite sequence that converges to square root of 2, well, this'll converge to square root of 2. I mean, the more digits we know after 414, the more we can write down, but that sequence where each number adds another digit from the square root of 2, that is an increasing infinite sequence of rational numbers that converges to the square root of 2. We could just as easily find infinite decreasing sequences of rational numbers that converge to 4/3 or to the square root of 2. We would just look at things from the other side instead of from the downside. However, not all sequences are useful. Not all of the sequences that converge to 4/3 or that converge to square root of 2 are useful. So let's talk about what kinds of sequences are useful. A sequence x1, x2, x3, dot, dot, dot of rational numbers is Cauchy if given any epsilon, oh, let's write them differently. Given any epsilon in the rational numbers with epsilon greater than 0, there exists a positive integer n of epsilon such that the absolute value of x sub I minus x sub j is less than epsilon when I and j are greater than n of epsilon. The heck does this say? What does this say? Okay, so I pick some teeny tiny number like 0.1. It's a rational number that's positive. There is some n such that the distance between any two of these numbers is less than 0.1 whenever I get big enough. So if epsilon is 0.01, then n of epsilon is greater than if epsilon is 0.1. What does this mean? This means that the terms approach each other. This means that the further out I go, the smaller the differences are between successive terms. And if I want to make the differences between the terms 0.00000001, there is an n that allows me to do that. And after I reach that n, after I get so far in the sequence, all of the terms are no further apart than this number. By definition, two Cauchy sequences are equivalent if the sequence obtained by interweaving them is Cauchy. So you and I may have come up with 1, 1.4, 1.41, 1.414, and so on, or we could just as easily have done 2, 1.5, 1.42, 1.415, and so on. This converges to the square root of 2. This converges to the square root of 2. The sequence obtained by interweaving them. These two are equivalent if the sequence we obtain by interweaving them is Cauchy. So here's the kicker. A real number is an equivalence class of Cauchy sequences of rational numbers. Sorry, that's just flat out sloppy. It is an equivalence class of Cauchy sequences of rational numbers. So we would say that the square root of 2, the square root of 2 is the equivalence class of that sequence. Every sequence that's equivalent to that is in the same equivalence class, and the square root of 2 is that equivalence class. Because we can pick any of those sequences, and they do the job. There are some notes that I will make about that. 3 of them, in fact. One is that the equivalence class of x sub I is less than the equivalence class of y sub I if the equivalence class of x sub I is not equal to the equivalence class of y sub I, and x sub n is less than y sub n for n greater than some number, where n is some whole number. Yes, that's a W. Golly gee. In other words, one real number is less than another if they're not the same, and once you get to a certain point, all of the ones over here are less than all the terms of this sequence are less than all the terms of that sequence. 2, and this matters if S is a non-empty set of real numbers and S has an upper bound, then S has a least upper bound. It's a property that you visit and revisit in Math 324 real analysis. If you have a non-empty set of real numbers and that set is bounded above, meaning that there is a number that is greater than all of the numbers in your set, then S has a least upper bound. Greater than or equal, yes. If you have a number that is greater than or equal to all of the numbers in your set, then there is a least upper bound. 3. Every Cauchy sequence of real numbers converges to a real number. Hashtag no holes. There are no holes in the real number system. The real number system is beautiful for that reason. And those are the notes I wanted to give you about real numbers, and we can certainly talk about that when we gather. Next up, arithmetic.